Yeah.
I grew up in Dresden.
Oh yeah, what town?
Teaneck.
Oh, Teaneck is very nice.
Well, worked for me.
Yeah. No, I
Wasn't really
mean,
my call, but
no, I know, but I'm just saying of all the towns to grow up in Jersey, Teaneck is a good one. I'm in Montclair, which is nice, but terrible commute. It's actually, no, it's not usually bad by driving. Something happened today, like something severe must have happened. I got an email from Brendan saying that he's not going to be able, like he's stuck in the same, so something went down. All right, so what I actually want to do today is I'm not gonna, all right. I just actually want to, it's actually a perfect slide. Okay, oh yeah, share screen. I think I have to. I will share my screen. Today's lecture will be focused on a I should be, yes. Yeah, full screen. Okay, so this is a really good, sorry. Turn my volume up if I can. Sorry, it's very hard to control these things. Just so I hear if there's any questions. Yes. The XOR problem, which is a really great way to understand right. Oh, that's not it. There we go. Right, so the XOR problem, this is like the classical problem that is posed to justify the need for neural nets. And so, first of all, I don't know if you guys are familiar at all with logic gates. I don't know if they teach you guys, but you know, there's AND gates, there's different types of gates. So there's OR gates. I'm not going to write out the truth tables. There's AND gates. Then there's NOR, NAND, and then XOR is this special one that we're going to cover here. So, so XOR is an operation between two binary inputs. So a logic gate, which is basically how computers work, is with gates that are implemented by transistors. So a gate has two inputs, two binary inputs, importantly. So X1 and X2 are binary. And so there are four binary digits. There are four possible combinations of inputs. And so an OR gate would be if one of them is, if X1 or X2 is 1, then the output is 1. An exclusive OR is an OR, except that the last element here, the situation when both the inputs are high, evaluates to a 0. So XOR means only one of the two inputs can be on, right? So binary means on, off, low, high, 0, 1, however you call it. So an XOR is a logical operation that has this kind of input-output relationship. And we can plot this, this, this data set, if you can call it that, is 4 points. So this is X1, right? The horizontal axis is X1, and the vertical axis is X2. And then the number here, the label, well, this number tells you the value of the function. So this is a 2D function, right? It's a 2D function. that is only defined over these 4 discrete points. And so as a picture, this is 0. This is 0. I'll do this. So this would be positive, positive, negative, negative, right? So it's negative. The output is 0 if both the inputs are the same. So if both inputs are 0 and if both inputs are 1, the output is 0, and otherwise, so green means 0, low, and orange means high or 1. And so the question is, how, if I want to separate these two classes, right? Hopefully, do you guys see that this is not linearly separable? Is that obvious? Right? There's no hyperplane that I can draw here to separate these, no matter how hard I try. And so I think the first question that I'll pose to you is, what kind of, for this problem, and this is a simple problem, and yet it doesn't have a simple solution. So what will the decision boundary for this problem look like? What's the shape of the decision boundary of this problem? You know, we agree that it cannot be a line, right? It cannot be a hyperplane. There's no way to separate green from orange with a hyperplane. And so my question to you is, what should our classifier look like geometrically?
What if you took it down?
Yeah, but hold on a second. Yeah, that's the topic of today's lecture. So the answer that was suggested in class is, what if we put it into a higher dimension? But we're getting there. But I want to stick to the geometry of this problem first.
What question? Can you have like separate, you say circles that are used that qualify to the same output?
Circles?
So let's say you have like 4 classifiers, right?
Mm-hmm.
But 2 of the classifiers are the channels of a parent classifier.
Yeah. So right. So that's definitely one way, right? So and what's interesting is that there's mathematically, it seems like what you guys are suggesting is really different, but it's actually the same, which is interesting. So yeah, so I think what you're saying is something like, let's first have one classifier. I don't know, I'm just gonna say, let's just make one classifier that is basically saying, everything above this is an orange, everything below this we don't know yet. And then maybe have a second classifier, right? Now, here's the thing though. To go, you have to make 2 decisions here, right? Yeah, it's 2 separate classifiers. The problem is that these 2 operations, these 2 decisions are inherently not, together it's a nonlinear operation. You cannot, and this is the problem, you cannot combine these into a single linear operation. What I mean by that is, you are going to have to make, so like the algorithm will be something like, I don't know, I don't use flowchart language, but I'm going to try to do it here. It's like, is it above, let's call this W1, let's call this W2, right? So I'm going to say, it's very informal, it's not mathematical, it's above W1, right? And again, I don't really know how flowcharts work, but if it is, then say y is equal to +1, right? We're set, because now we know that we're just 1. If not, then you have to ask another question. Is it above W2? And then if it is, and now we have a decision on both sides. If it is above W2, then it's a 0, and if it's not, then it's a 1, right? So this is the kind of two-step two-step algorithm that could solve this. See, the problem with this kind of approach is that it's totally sensible for a simple toy problem such as this, but when you're getting into thousands and millions of features, it's obviously not. First of all, we hand tuned it, right? Like we looked at it and we kind of we inspected the problem, which you can't do in high dimensions.
You're also like losing data as you train that first step. You have to cut out whatever was called one.
Yeah.
And no longer use it for determining W2.
Yeah, right. Yeah, I mean, that's right. This is, we haven't even, that's right. We haven't even touched the issue of training and test data. And so this is a heuristic approach that works for this problem, but the point is that what we want is something that, just given X, applies some function to it that produces Y and still has that character, that truth table. The truth table is this table here. It's like when you're designing, like if you're designing a circuit, at least this is the way I was taught in undergrad. What you do is at the very beginning, you have to it's a combinatorial deterministic thing where you have to determine for every possible set of inputs, what should the output be? So like electric circuit is not like a learning algorithm at all. There's no learning, it's all hard coded. And so what they would do is they would have us write, it'll be much more, it'll have more inputs than 2 and maybe more outputs than 1. But you would sit down and you would literally have to figure out what the output should be for every possible combination of inputs. And then you would have to build a circuit to implement that, which is kind of what that flow chart is doing. The problem is we don't want to have to do that. We want to have a general purpose algorithm that can take any X and given enough data, output Y. And so, for example, maybe these are like clouds of points. Well, hold on a second. You guys haven't answered my question though. I just realized. What is the shape or what is the structure of a classifier that separates these two classes? A parabola? Yeah, I mean, sort of. Yeah, hyperbola. That's right. It's a hyperbola. It's okay. Hyperbola is right. So a question I asked once on the midterm for this course, which you're not gonna, is can a radial basis function solve this problem? So remember, radial basis function is like you're just looking to see points, like which class are you closest to, which is an interesting for you. I encourage you guys to think about that. But hyperbola is the one to me that makes the most intuitive sense right here, because you can draw, so the decision boundary, everything that's kind of outside, I'm just going to call this outside the hyperbola, belongs to the green, and everything that's kind of inside belongs to the orange. You guys know what degree polynomial that is? Or any ideas? Or nope, not 1 over X. That's a good guess. It's okay. You guys know, I think it's just 2, right? I think it's just a degree 2 polynomial. It's just that you have isn't that hyper? Yeah. Right. So it's not even a high degree polynomial, but in general, so I think last class I was mentioning is universal approximation theorem. And I should look this up before saying in class, but I don't know what the proof for the universal approximation theorem is, but I think it probably has to do with Taylor series polynomials. But in general, it's not a good idea to be fitting polynomials in high dimension. So even though hyperbola could solve this problem, what I'm trying to argue to in this class is that it's just not a very robust methodology. for solving this XOR problem. And so rather, what we're going to do is we are going to construct a very simple neural net to solve this. And we are actually going to come up with the coefficients ourselves. I mean, I'm going to tell you I'm going to show you the coefficients that can be chosen ad hoc, and we'll convince you that this problem can be solved with a single hidden layer. So you have your two inputs. So x1 and x2, and we're going to have just a single hidden layer with two nodes, and this will be h1 and h2. And we're going to have obviously a single output, which I'm going to call y. And we are going to draw a connection between every input and every 2 by 2. So we're going to have, and we're going to call, so there's 4 weights. I think I have a slide for this. Let me see. Yeah. Okay. Right. So what I'm drawing on the board is what's on the slide. So we have a very simple rather neural net that has our two in. So if, in case it's not clear, the inputs go on the input layer. So these are your 2 binary digits. So x1 you specify. So at the bottom layer and the top layer are the data. What's in the middle is what's being learned. And so the 2 pictures here are equivalent. It's just that this is a vector, scalar, and these are all scalars. And so we have, I guess 4. I mean, there's 2 transformations that we have to learn here. There's a transformation from the input to the hidden layer, and then there's a second transformation from the hidden layer to the output. Now, this transformation, you may think it has 4 parameters, but it actually has 6, because you have, let me just cover quickly. Well, actually, I'll do this in the board. So, okay, so H1, I'll switch. I'll stop share for this. So, right, let's look at how we construct H1. So H1 is going to be, it's going to have contribution from each of the inputs. So I'm going to call this W11 X1 plus W12 X2 plus I'm going to add a bias term, which I'm going to call C1, just the coefficient. And remember I said that I'm going to apply a sigma. I'm going to apply an activating function to this. So an this is the nonlinearity without use some OT. This is that activating function sigma. And so remember I said the sigma could be, sigma could be a sigmoid. Here we're going to use what's called the rectified linear unit, which is very popular nowadays. It's denoted by ReLU. So this is 0. So if I have my x-axis, this is the horizontal axis here. So this is 0 here. And this is the output. So the output of the ReLU function is, and it stands for rectified linear unit. And it's the max operation between 0 and x. Maybe not call it x, just call the argument set. Right, so the goal of these, first of all, why do we need these activating functions? Well, we need them because otherwise all we have is a linear classifier. And we've already determined from looking at this problem, the linear classifier is not going to solve our problem. And so the activating function that we're going to be using here is basically looking at the input. If the input is negative, you output is 0. If the output is positive, you output itself, right? So if the input into sigma is positive, then this is just a linear function, which is nice. And so there's a couple of things that I'll mention here. Sigmoids and tan H's, hyperbolic tangents, have fallen out of favor, I guess, a little bit. Part of the problem is that what we'll see is that to actually opt to learn in neural net, you have to apply the chain rule over and over. You basically, the way neural nets work is you look at the error up here between what your neural net produced and what you wanted it to produce. And then you differentiate that with respect to all these weights. And so what you end up doing, so what ends up happening is you end up differentiating. You end up doing, so the chain rule, remember, it's a product of gradients, right? It's a product of derivatives. And what ends up happening numerically is that when you end up having to multiply a lot of small numbers, like you end up taking a product of a lot of small numbers. And that causes problems because you get this issue where it's called the vanishing gradient problem. You don't really have to understand what it is, but basically what happens is that if a lot of your gradient terms are like computed over this flat range, so the gradient, the derivative of the sigmoid is 0 in a lot of places here. You know, it's only non-zero basically in this region. And so this property of the sigmoid, the fact that it's flat for such a large extent of the input, kind of exacerbates this vanishing gradient problem, where your gradient kind of your gradient goes to 0 and the learning stops. And so very informally, you are in machine learning, you're essentially finding the W's. So in this case, to minimize some error. And the problem is that that error term, and then what you end up doing is you end up differentiating that error with respect to W. And these kinds of functions, activating functions, give you fits because a lot of times the result just goes to 0, either numerically or actually. And so this function has kind of been introduced, this ReLU function has been introduced kind of like an antidote to that, where as long as your input is positive, the gradient, this is just like a linear, so linear functions have nice behavior, right? Differentiating a linear function is easy. And so this function preserves the linearity as long as your input is positive. And it evaluates to 0 if your input is negative. The other nice thing about this is that it's still I think it's it's still differentiable at 0, right? It's not like this kind of function, the absolute value function is not, because the limit from the left and the limit on the right. Actually, I don't know if this is differentiable at 0. Not so sure, because the limit on the left is 0, the limit on the right is whatever the slope of the curve is. But nevertheless, the only at this one point do you have this whatever call it non-smoothness. And so this is a really nice activating function to work with. And so now I'll go back to the slide in a second. So sigma becomes the max of 0 and this whole thing. And what I'm gonna try to show you today is I'm gonna try to show you that if, as long as we pick our W's and our C's appropriately, we can solve this. We can solve this XOR problem quite easily. Okay. All right, so next, so I don't spend the entire lecture writing stuff out, I'll show you the equations on the slide, right? So H1 is, it's this ReLU activating function of just a linear way to, a linear combination of our inputs. So what's in the parenthesis, what's to the right of the comma is just a linear function of the x's. And then again, the C1 is just a coefficient. H2 is the same thing, but now we're gonna allow it to learn a different mapping. So remember, Amilcar suggested that we should have two linear. That's kind of what this is doing, right? It's learning two. It's learning two decision boundaries. You can think about it that way. And then at the end, y is gonna, so this is cascaded, y is just gonna be a linear function of the h's. We don't even need, what you're gonna see is you don't even need a nonlinearity on y. You can, h1 and h2 are gonna be linearly separable if you choose your coefficients correctly.
But Professor, your decision boundaries in this case were C1 and C2, or
yeah, so this sort of, yeah. I think it's maybe minus C1 and minus C2, but you're gonna compare, you're gonna at the end of the day, you're gonna, so the final decision is this, and you're gonna evaluate, compare that to 0. And then in terms of, if this evaluates to a positive number, then H1 is that positive number. If it's negative, it evaluates to 0. And so this can be written more compactly as a set of vector equations. So H is now a vector that has two elements, H1 and H2. And so this is like, we have a W. We can write our, so there's a W, capital W is the transformation from the input to the hidden layer, and the small w is the transformation from the hidden layer to the output, right? So this is basically, so that's what this thing is doing here. It's just multiplying your x's by a matrix, and that matrix, the 4 elements of that matrix are these 4 arrows here, right? So the strength of the 4 arrows is just the value of the coefficient. And then, so you do that, right? You apply this matrix operation to your x's, and then this is now a vector. This is now a vector of 2 elements. And then each of those elements you compare to 0. And then you take the max, and that's the value of your hidden layer, of your hidden, your hidden units. And then once you have your hidden units, you just apply a lowercase w, which is just a regular linear classifier with an offset, and you get your output. And so what I'm going to show you on the next slide is that it's not difficult to come up with coefficients for the W's, the C's, and the B's to solve this problem. And so our goal here is to find the coefficients of W, C, and B such that this whole mapping, so essentially what Y is, it's a function of our inputs, and it's parameterized by the weights and the offsets. And our goal is to figure out what these parameters should be such that Y always matches the XOR truth table. And so here is the solution. And I'm gonna do my best. I'll take a sip and let you stare at it, see if you get any intuition. So probably place to start is the pictures here. So this is just the original problem. And this is now your data, but expressed in the space of your hidden units. And so what you hopefully notice is that this data point, the 0, 0, is still just in this, it's evaluated. Oh, let's see, how do I explain this? Well, first of all, it is now linearly separable because now you can draw a line between the zeros and the ones. And so what's happened is that both inputs that evaluate to 1 are now mapped to the same point in H space. And so I think we should actually evaluate this on the board because it's such a simple problem that we can just explicitly compute it and see that we do in fact reproduce the XOR relationship. And so let's take the case where and so our matrix, actually I have it on the board. So we use this. Right, so our W matrix is all ones, which is nice. So you're basically just summing. What you're doing is you're summing the 2 inputs together. So there's not much logic in here. The logic I think is in the it's actually in the offsets, which is interesting. So this is our actually, because it's on the board, I'm going to use it. So H1 right, so H1 and actually I should put the max off, make some room for the max operation. So this is the max operation applied to each element of this column vector. So basically this is what it looks like. So you take your 2 bits and you sum them up, and then you add either a 0 or a -1 to it. So now let's make our truth table on the board. Turn off this. Oh, I'm not sharing. Oh, oops. I should have been sharing. All right. Right. So now what I want us to do is to stick in all 4 combinations of the x's into the column vector and see what comes out of y. So if x1 and x2 are 0, what's the value of h1 and h2 here? Right. So obviously anything multiplied by 0 is 0. 0, 0, right?
Yeah.
And so, hold on. Yeah, that's right. Right. This will be 0, 0. So what that means is that this is 0, 1, 0, 1. So we are doing this point, right? This point here. So this is x1. Do I have 4 different colors? Oh, goodness. So this is x1 and x2. So what we're doing, so what I'm trying to demonstrate on the board right now is I'm trying to warp this. It's like a coordinate transformation, right? Where this point, what did I have it as before? I think I had. This point, and again, I still have, now I'm gonna have 2's in here, so I'm gonna make 0, 2. And so this point here evaluates to an h1 of 0 and an h2 of 0, so it just sits here. What about when x1 is 0 and x2 is 1? What will that evaluate to?
1, 0.
See. So the top one, so 0 plus 1
Something.
plus 0. So this is a 1, right? And then the bottom row is going to be the same value, but now the offset. So 0. That's what you said, I think, right? 1, 0. Yeah. So now we were doing this point here, 0, 1. And so 0, 1 has now been mapped to 1, 0. It's interesting. What about 1, 0? Something. 1.
I know from your slide it definitely.
Hold on a second.
Really take it slow.
1 plus 0. That's 1, and then 1. Right. It has to be. It has, yeah, right. It has to be the same because the -1 just pushes it to 0. And so we did this point. We did this point. So it's an orange, and it evaluates again to this point. So these are. I'm going to make this marker larger to show that, indicate that this is actually 2 points overlaid. And what about 1, 1? What does 1, 1 evaluate to? 2, 1, 1. Yeah, 2, 1. 2, 1. And so that becomes, and this is, now you can see that it's being, and so now we can draw, I mean, it's kind of, we can draw a hyperplane now between right, and so this is now our data in this new space. And so this is this space has nonlinearities in it. That's what allows us to separate these problems. Right. And so now we've gone on the board from here to here, and then we still need weights for the W's. And it's not difficult. You just need to figure out the slope and intercept. So you can choose weights of 1 and -2. I don't think I showed it on the slide, but it's not difficult to see that these weights on H1 and H2 will separate the two classes now. See, right. Okay. So the I guess before, let me see. The this is a really nice example for a couple of reasons. One is this ReLU activating function that we use is super useful, and it's basically used in all the computer vision and natural language algorithms. I guess it's one of the ingredients that has made deep learning work so much better over the last 10 or 15 years, in addition to larger training set sizes, probably the larger data set sizes, and just, you know, obviously stacking of many hidden layers, but also this activating function does apparently help with learning. And so, right, what I wanted to say at this point is that what we just did in class, which is we looked at the problem and we tried these coefficients and we verified that they do indeed solve a problem. It's not possible to do that in, you know, on any real problem. On any real problem, we need to somehow come up with a statistical criterion that allows us to optimize the W's and the small W's and the C's and the B's automatically. Like, we don't want to have to do this for every problem. And so I guess I skipped over some slides because I wanted to start with this example, but I'll go back now and hopefully, right, this is where we were last time. And so a lot of this content we covered in this example. And so obviously your inputs go on the bottom, your outputs go on the top, and the hidden layers, that's where the interesting stuff happens. The hidden layers are learning nonlinear features of your data. And so in the case of like vision, or for vision, these nodes will represent, like, they'll either be on or off, let's say. And so they'll be on if there's a face detected, and or if you know, there's a bicycle or whatever. Like, these, they represent more abstract things than just edges or something like that, especially the higher up you go. And the W's, all these W's and the V's, they are all learned by trying to force the outputs. So in this picture here, by the way, models the case where you have a 4-class problem, right? At least a 4-class problem, can actually be more. And so what you do when you train these things is you run an algorithm. It's called backpropagation. You don't need to know much about it other than to know that it's essentially just, you have a cost function, which is measuring how close the output is to the desired output. So in our case, the desired output is that these two should map to a 0, these two should map to a 0, and these two should map to a 1. And so with the neural net, during learning, what's happening is that you're just trying different weights. And if the weights if the weights bring you closer to the desired solution, you go in that direction. If they bring you further away, you kind of switch course. That's basically all it is. There isn't really any new profound insight in the world of optimization. You have like the way I always talk about cost functions, it's a bowl, it's a quadratic bowl, and you're trying to get to the bottom of the bowl, or if it's a maximization problem, you're trying to get to the top of the hill. And all you're doing is following the gradient. This is, by the way, what like animals do, what like when a fruit fly follows, tries to smell something and they try to get to the food. That's all they're doing, is they're just like, they're flying in the direction of the gradient, basically. A dog will do this. You see dogs do this all the time with smell, right? When dogs smell, they're scanning the directions to figure out where there's the largest change, which that's what the gradient is. It's a vector that points in the direction of the most change. The other thing I'll say, let me see, I don't want to zigzag too much. Maybe I'll finish, then when I'll get to the gradient descent slide in a second. Okay, so I'll just walk through each of the layers. So the input layer is determined by the dimensionality of your data. So if you're doing images, it's just the number of pixels you have in your image. If you're classifying waveforms, which we haven't really covered here, like if you're trying to classify speech or EKG or whatever, you have one input node for every sample in your signal. And so, all right, the second bullet is actually pretty important. So choosing the input is really is very critical, and you can go wrong here if you either choose the wrong features or if you pick too many of them. And so historically, the way a lot of thought has been put into how to choose the nature of these. So for example, maybe what I'll do is I'll draw, sticking with the waveform example, if let's say you measure, and the BME example here, you measure an EKG, and your job, this is what I guess the iPhone now works, but they're still measuring an EKG. They're just doing it optically, but Apple Watches, these are called the iPod. So if you have an EKG, you'll have something like this. I don't know. And then these are your heartbeats. This is your pulse. The period between successive heartbeats. Oh, Robert, I'm just drawing an EKG on the board. Nothing to see here. And so the point is that your EKG waveform can be sampled, right? You can sample it, once every whatever few milliseconds, and then you can pass each of those samples in, to be your input. XT, and that is, this will be your input layer. Because every sample of your EKG waveform is an input. Generally, that's not a good idea. Can anyone tell me why it's not a good idea to do this? What's that? Can anyone think of why? Like I measure let's say my EKG is like, let's say more than just two cycles, right?
They have to be the same size, no?
No, that's a good guess, but that's not really why. So actually, this is a problem in machine learning. It's a problem in speech a lot, because two people saying the same thing will have different durations, right? And so that is a problem, but that problem has been solved in pretty heuristic ways. Like they just like pad stuff with zeros or something like, but that is a problem, yes. But that's not really why. There's a deeper reason why just sampling my EKG. Robert, I'm doing this for you, buddy. And perhaps, no, Brendan's not on the call. Brendan's stuck in traffic. All right, so there's an EKG waveform on the board. And what I've done is I've sampled it, and I'm asking the class why it's probably not a good idea to have every sample be an input feature here. Noise? That's a good guess too. It's not, and there's an even deeper reason. Noise, sorry. noise is definitely a consideration, right? If your waveform is noisy, you probably want to remove the noise before passing it into your neural net.
Too many zeros.
Too many zeros. So the thing I'm going, and I'm not expecting you guys to actually know this, but the thing I'm going for is that there's a lot of autocorrelation in the signal. So what does that mean? Autocorrelation means a signal is correlated with itself. In other words, if I know the value, maybe it would have seen it more if I did something like this, if I made them closer. The point is that if I know the value of the signal at a time point, I have a lot of information as to where the next sample would be. In other words, the information that is contained in this sample is only a little bit more than this one. And so by passing it here, what I'm doing is I mean, pretty much I'm on the, this could definitely lead to overfitting because I'm putting in redundant features, and redundant features it's wasteful, right? So I could probably I could either downsample this, or I could do something like, there's something called a time frequency representation, which is kind of like an image. You may have seen this. It's like you do a fast Fourier transform on this. You have a spectrum. You have like this is a color image generally, but the point is each of these is a spectrum, and you do it across time, and that will capture a lot more information. And there's different ways of basically taking this and kind of distilling it to a small set of numbers that still captures all the information in that waveform. That's really the key. You want to get all the information out of that waveform in as few samples as possible. So at the very least, you should sample this at the Nyquist rate and not any larger. This problem, it seems fundamental, but actually classification of waveforms is like, Google came out with this thing. I'm trying to think of. There's a popular algorithm called WaveNet. I think it's called WaveNet, and it's a Google product or whatever. And they try to solve this with something called convolutions, but this is a big problem. Is that waveforms, you want to capture the temporal information. Like there's information, and this is a sequence. It's the other thing that should be. Well, it's probably not obvious to you, but the big difference between an image and a waveform is that an image is a static thing, where the relationship between pixels, like it's kind of meaningless. Like if you scramble the pixels of every image with the same way, you would end up learning the same things, right? It's just, yeah, it's true.
So what about the edges?
I see. Yeah, I mean the edges would appear elsewhere, but what I'm saying, okay, maybe it's not a great example, but the point is that there isn't really I guess maybe you guys could argue this point with me. Is there any, if you have an image, I'll get out of here in a second, right, and you have the claim I was trying to say, and a lot of this stuff I ad lib, and so it's totally possible that I say things that are just wrong. But what I was trying to argue is that in an image, there's no order information, I guess, but there is spatial representation. There's a spatial representation, yeah. But and I guess you could do the same kind of thing where formally the way that this is, like if you have the probability of the function at x of t, it's going to be, it's going to be a function of x of t minus 1, right? And I guess you can do the same thing there. It's like the value of a pixel is correlated with the values of neighboring pixels. So maybe this is not, it's not actually the image versus waveform in this sense is not the best analogy. Whoa. However, there is something that is special to waveforms, and this motivates the use of what are called recurrent neural nets for my computer sees it. I don't understand why the projector doesn't. For example, in speech, the phoneme, the sound is being heard right now is definitely the order that you receive the data in is important, is what I'm trying to say. And that's a property, filament. You turn it this, I cannot believe this is a technology where if you turn off one of these, you have to wait for it to cool down before you turn it on again, I think. But the order of the wave of the inputs matters, which is what I'm trying to get at with this waveform. And so you want to capture oh, it's coming up. You want to capture the information as waveform with as few numbers as possible. And actually, what I've worked on problems where we have to measure heart rate and heart rate variability. And what you actually do, there's this algorithm that's basically it finds the peaks, and then it measures it finds the peaks and measures the time period between them, and that becomes like, and the interval between peaks becomes your feature, which is for the case of predicting heart rate very useful. All right. So that's your input layer, and the input layer, choosing it is very important. There's something you may come across this term end-to-end learning, which is very popular nowadays, which is like, no, I'm just gonna give it the raw data, and I want the network, I want the model to tell me what the right features are. This is only possible if you have a ton of data. Like you can do this with images because there's Google Images, which has billions of examples for you to train on. But end-to-end learning means that no more humans crafting features. Just make a big network, and essentially what it's going to do is the hidden layers will learn this for you. The hidden layers, you say, no, I want the hidden layer to tell me, to be able to measure this interval for me, and have that be the thing that drives a decision as to whether this is an arrhythmia or not. Okay, the hidden layer. So here, the only thing I'll say here, because we've covered all this, here are three popular activating functions. The hyperbolic tangent, which is like the closest that a smooth function gets to a step function. This is the sigmoid, and this is the Rayleigh function here that we are looking at, right? So these are three commonly used activating functions. The choice of activation function, you have to think about what your problem is, and also you have to consider where your loss function is. And we haven't covered loss functions really yet, so I'll delay that discussion. This is the activation function that we use. It's very popular. It's called Rayleigh. There's a cousin of it called ELU, where it can go a little bit into the negatives. So if for whatever reason you believe that one thing about this, if your network only has Rayleigh activating units, you won't have any negatives appearing, right, in your outputs. It's not like because all your all your hidden layers will rectify. And so if you feel like you need a distinction between negative and positive, maybe this isn't a good thing. For things like images where you're like, is this a face? Is this a face? Yes or no? You don't really need positive and negative necessarily, but just something to consider. And then the output layer, that's the thing, that's obvious, it's self-explanatory. That's your Y, that's your estimate of the label. And so the way it generally works, so as I said, this problem has 4 output nodes. And so if you take the common case where the nodes are either on or off, right? There's different ways of representing an output. So one way is just binary. In which, did you guys know how many combinations of numbers 4 binary digits give you? Any ideas? You guys know if I have 4 binary digits, each of these are either 0 or 1. This is what I want. This is my output layer. You guys know how many possible values this output layer can represent? 2 to the, what's it? You said 2 to the 4th. One you said, and you said what?
The handshake rule.
The handshake rule. So it's 2 to the 4th is right? So it's 0 up to 2 to the 4th minus 1. So 0 to 15, right? Basically in binary. However, in many cases, the way that this is, the structure of your network determines what values can actually be taken. Oftentimes, what's used is something called a one-hot encoding, where one-hot encoding means that you have in this case, you only have 4 possible values. So only one of the 4 bits will be allowed to be on. This is another one of these buzzwords, one-hot encoding.
You're switching the order, that would really bother me.
Yeah, sorry. Yeah, no, I'm not going to switch the order. I did it again. It's a compulsion. Right. And so one-hot encoding just means that. And so, here's a great question. So this is one-hot. What's wrong with having the network? What's wrong with having the Ys just be 1, 2, 3, 4? Why do we do this? This seems wasteful, right? You have more connections. Anyone know why 1, 2, 3, 4 is not a good choice? And why do we bother with this one-hot encoding?
Well, with this, it's easy to map to whatever you want, right? No.
So why, like, if we have, let's say we have 4 classes, right?
What do you mean?
Yeah. So what I mean by that is if I have, let's see, let's think of a 4-class machine learning problem. Okay, hold on. Let's think of, what's that? Eye color. I'm gonna stick with the. There's gonna be some overlap. Just bear with me here. Metastatic. Okay. I know that malignant and metastatic are probably heavily overlapped. The point is you have 4, right? What's wrong? And I need to assign a value of Y for these 4 classes. What's wrong with doing this? Why don't people do this? Why don't we let Y be 0, 1, 2, 3, or 1, 2, 3, 4? Why do we do this? And I'm not expecting you guys to, again, this is one of these things that it's kind of a, it's like one of these tricks of the trade thing. Like it's not, I don't think you'll see this in any textbook. Why do we do on? We generally, for this situation, again, there's probably better examples to do this with. Maybe, let's see, let me think of one. This is actually not a good example for this. These no tumor. Let me think of another. Yeah, I think let's do the eye color, just because it works for this. What's a popular? Let's say brown, blue, green, hazel. Are there other eye colors, by the way? Like gray.
Great.
So, but this is actually good. So here, it's definitely a bad idea to do 1, 2, 3, 4. Anyone know why?
Is it because you don't want to like kind of sort them or order them?
Yeah,
So it doesn't
exactly.
have to be a
There's
thing.
no, these are not ordinal. These are not, this is not an the term that is used here is ordinal. This is not an ordinal variable. There's no ordering among brown, blue, green, and hazel. And the problem is that what your network will do is it will somehow learn to give green and hazel. Green and hazel probably are same.
I'll say it works.
Yeah, it still works. You know what I'm saying. The point is that it will implicitly learn that somehow green and hazel are on one end and brown and blue on the other end. That's not true, right? In general, when you have 4 classes. Whereas here, you see these are just 4 orthogonal classes. There's no ordering.
Does that mean it can be beneficial to do 1, 2, 3, 4, like the cancer example?
Yeah, I was just gonna ask, why was it?
Yeah, that's why for the cancer. So here's the real. I don't know why this keeps happening. The real problem with the 1, 2, 3, 4 is it's not. Let's say you want to do 1, 2, 3, 4 for the cancer example. If you have your 4, let's just in this case you can just have one output variable. Let's say that's just an integer or a continuous number. This is my this is my input node. And then you have then you have your hidden, then you have your image at the very bottom. The problem is that what ends up happening is it's difficult to find a learning rule. So the way learning works is you have your first scan y x1, and then the first label, and then the second image and the second label. And you're going through them kind of as a training sequence, and you're just going, okay, let's get this example right, and this one. What happens is the kind of gradient descent algorithm that we use to learn the weights, there's nothing in there that will magically get that ordering. It will just, all it cares about is errors. Like, did it, for all it cares about is like, if this is the truth, 1, 2, 3, 4, and this is the prediction, 1, 2, 3, 4. It wants to put a lot of mass on the diagonals, and it wants to put not a lot of mass on the off diagonals. But there's nothing in there that will somehow make the metastatics and the malignants kind of map to similar values necessarily.
Isn't that kind of the opposite of what you just said of why it would be a problem? You said it's assigned
Sorry.
order in cases where there aren't order.
So, no, but in this case, there is an order, right? What she's saying, or what's being asked is, in the brain scan example, there is an order. What I'm saying is there's nothing in the learning algorithm that will, the learning algorithm just tries to match 1s to 1s, 2s to 2s, 3s to 3s, and 3s to 4s. But if you have something like, let's say that the boundary between 3 and 4 is 3.5. If something is here versus something is here, it's not actually, if you actually inspect what's learned, this one will not end up having, this one will not be have more metastatic qualities than this one, basically. Because the, yeah, this is tricky. So what I can tell you definitively is that if you're gonna do the 1, 2, 3, 4 thing, the name for that is ordinal. It's sometimes called ordinal regression because technically you have. And what I can tell you is that a neural net does not do this unless you program it, right? So a neural net will not do this. There's actually a way to implement this kind of property into it. So I realize I've gone over, but because this is a really great question. So I guess what I'll say is, if you have the 4 inputs, part of the problem is that it will, what ends up happening, I think, is that if filled in is 1 and empty is 0, it ends up sometimes learning weird things like this, where, okay, if these 4 represent probabilities, the probability, like given an example, the probability, like if the probability of a benign is 0.9, and the probability of no tumor is 0.9, then these have to be monotonically, or it's the other way around, 0.1, 1.2, 0.3, 0.4. And so if they're not monotonic, the problem is that a neural net is basically learning probabilities, and the problem is that there's nothing we can do for out of the box. The probabilities that are learned over the output nodes are not guaranteed to be monotonic, and then you get into these weird situations where, like, in the extreme case, you'll have, like, let's say you have 4 classes. We have no tumor, you have benign, you have malignant, and you have metastatic, and you'll get into a situation like this, where these are the 4 probabilities. This doesn't make any sense. If the algorithm is being confused, right? This should not happen. And so when you want to do this 1, 2, 3, 4 bit, you got to use something called ordinal regression. There's a ton of information online, and this is something that I've had, because in BME these orderings are common. I've had to do that. We'll see you guys on Wednesday. Thank you for letting me go over.
Thank you. Have a good day.
Bye, Robert.
Thank you.
See ya.